Voyager 1 is the most distant spacecraft ever sent from Earth, currently racing through interstellar space at 38,000 miles per hour, more than 15.5 billion miles away from home. What makes this achievement even more extraordinary is that this technological marvel was built with 1970s equipment, launched when disco ruled the airwaves and personal computers were science fiction. In the summer of 1977, humanity embarked on one of the most audacious journeys in the history of space exploration, sending two identical spacecraft toward the outer reaches of our solar system. These were the Voyager probes, and their mission would fundamentally change our understanding of the cosmos while demonstrating the extraordinary ingenuity of an era that dared to dream beyond the possible. The story begins with a rare celestial alignment that occurs only once every 175 years. In the late 1970s, the giant outer planets of our solar system found themselves positioned in a way that hadn't been seen since the early 1800s, and wouldn't be seen again until the year 2150. Jupiter, Saturn, Uranus, and Neptune were arranged in the same general direction as viewed from Earth, creating what mission planners recognized as a once-in-a-lifetime opportunity for what they called the grand tour of the outer solar system. This planetary alignment was crucial because conventional rocket technology of the era simply couldn't provide enough velocity to reach the distant outer planets within a reasonable time frame. A spacecraft launched directly toward Neptune, for instance, would take decades to arrive using chemical rockets alone. However, the aligned planets offered something far more elegant: the possibility of using gravitational assist maneuvers, or what scientists call gravity slingshots, to accelerate the spacecraft from planet to planet, gaining tremendous speed with each encounter. The concept of gravitational assist was revolutionary for its time, though it built upon principles of celestial mechanics that had been understood since Newton. As a spacecraft approaches a massive planet, it falls into the planet's gravitational well, gaining speed. By carefully timing the approach and departure angles, mission planners could use the planet's own orbital motion to catapult the spacecraft toward its next destination at much higher velocities than would otherwise be possible. It was like catching a ride on a cosmic carousel, where each planet would swing the spacecraft around and fling it toward the next stop on the journey. The engineering challenges of the 1970s made this mission seem almost impossible. Computer technology was in its infancy. The most powerful computers of the day had less processing power than a modern digital watch. The Apollo program had demonstrated that humans could reach the moon, but that was a mere 3-day journey compared to the decades-long Odyssey planned for the Voyagers. Mission planners had to design spacecraft that could operate autonomously for years, making critical decisions without human intervention while traveling billions of miles from Earth. The Voyager spacecraft themselves were marvels of 1970s engineering ingenuity. Each probe measured about the size of a small car, dominated by a distinctive 12-foot diameter high-gain antenna that would become their most recognizable feature. This dish antenna had to maintain precise pointing toward Earth across vast distances while the spacecraft tumbled through space, requiring sophisticated attitude control systems that could operate reliably for decades. The engineering tolerances were extraordinary. Even a pointing error of just 2 degrees would be enough to completely sever communication with Earth when the spacecraft reached the outer solar system. Power was another critical challenge that showcased the innovative thinking of the era. Solar panels, which had powered most previous space missions, were useless at the distances the Voyagers would travel. Beyond Mars, sunlight becomes too weak to generate meaningful electrical power. The solution was nuclear power, specifically radioisotope thermoelectric generators that converted the heat from decaying plutonium into electricity. Each Voyager carried 3 of these nuclear batteries, generating over 400 watts of power at launch. This was cutting-edge technology in the 1970s, representing one of the most sophisticated power systems ever placed aboard a spacecraft. The scientific instruments packed aboard each Voyager represented the pinnacle of 1970s space technology. 10 different experiments were crammed into the limited space and power budget of each spacecraft, including cameras that could capture detailed images across vast distances, spectrometers to analyze the composition of planetary atmospheres, magnetometers to study magnetic fields, and particle detectors to sample the space environment. Each instrument had to be ruggedized to withstand the harsh conditions of space for potentially decades, something that had never been attempted before on such a scale. Communication systems posed perhaps the greatest technical challenge of all. The Voyagers would eventually travel so far from Earth that their radio signals would take over 22 hours to reach home, weakened to an almost incomprehensible degree by the vast distances involved. The spacecraft transmitted with just 22 watts of power, equivalent to a bright household light bulb, yet this faint signal would need to traverse billions of miles of space and still be detectable by Earth-based receivers. The inverse square law of physics meant that signal strength would decrease dramatically with distance, requiring unprecedented sensitivity in the receiving systems. NASA's solution was the Deep Space Network, a global array of massive radio telescopes that represented another triumph of 1970s engineering. These enormous 230-foot diameter antennas, positioned in California, Spain, and Australia, could detect signals so weak they contained less than 1/1000th of a watt of power when they finally reached Earth. The global positioning of these antennas ensured that at least one could always maintain contact with the distant spacecraft, enabling continuous communication despite Earth's rotation. The launch sequence itself demonstrated the precision required for such an ambitious mission. Voyager 2 lifted off first on August 20, 1977, followed by Voyager 1 on September 5. The naming convention was deliberately confusing. Voyager 1 was launched second, but would arrive at Jupiter first due to its faster trajectory. Each launch window was incredibly narrow, lasting only a few weeks. Miss the window, and the entire Grand Tour opportunity would be lost for another 175 years. The trajectory planning required calculations of extraordinary precision, using the limited computing power available in the 1970s. Mission planners had to account for the gravitational influences of multiple planets, the exact timing of planetary positions, and countless other variables to plot courses that would take the spacecraft on their epic journey. These calculations represented some of the most complex orbital mechanics ever attempted, requiring new mathematical techniques and computational methods that pushed the boundaries of what was possible with 1970s technology. As the Voyagers departed Earth, they carried with them not just scientific instruments, but also golden records containing sounds and images from our planet, intended as messages to any extraterrestrial intelligence that might eventually encounter these wandering ambassadors. This optimistic gesture reflected the bold vision of an era that dared to dream of interstellar communication and cosmic exploration on a scale never before imagined. The trajectory that carried the Voyagers through the outer solar system was nothing short of a masterpiece of celestial choreography, executed with 1970s technology that had never been tested on such an ambitious scale. As these twin explorers began their epic journey, they were about to transform our understanding of the giant planets in ways that no ground-based telescope could ever achieve. What followed was a series of planetary encounters that would rewrite astronomy textbooks and reveal worlds of breathtaking complexity and beauty. Voyager 1's first major destination was Jupiter, the solar system's largest planet, which it encountered in March 1979. The approach to Jupiter represented the first critical test of the gravitational assist technique that was essential to the entire mission's success. As the spacecraft swept past Jupiter, it had to thread a precise path through the planet's intense radiation environment while gathering unprecedented scientific data. The timing was absolutely crucial. Arrive too early or too late, and the gravitational boost wouldn't provide the correct trajectory towards Saturn. Miss the target by even a small margin, and the entire grand tour would collapse. The images that Voyager 1 transmitted back from Jupiter were revolutionary. Captured by cameras that represented the pinnacle of 1970s imaging technology. These were not digital cameras as we know them today, but sophisticated television-like systems that built up images line by line and transmitted them back to Earth as analog signals. The processing power required to enhance and reconstruct these images pushed NASA's ground-based computers to their limits. What emerged were photographs of Jupiter's atmosphere in stunning detail, revealing the planet as a dynamic, churning world of incredible complexity. The Great Red Spot, Jupiter's famous storm system, was revealed in exquisite detail for the first time. Voyager's cameras showed this massive hurricane to be a complex, multi-layered system larger than Earth itself, with intricate swirling patterns that had been invisible to terrestrial observers. The spacecraft also confirmed the existence of Jupiter's faint ring system, a discovery that came as a complete surprise to scientists who had never suspected that any planet other than Saturn possessed rings. This finding alone demonstrated the value of close-up exploration over distant observation.
Perhaps even more spectacular were Voyager 1's discoveries about Jupiter's moons, particularly Io, the innermost of the 4 large Galilean satellites. When scientists first examined the images of Io, they noticed strange circular features on its surface that initially defied explanation. Then came the revelation that would shake the foundations of planetary science. These were active volcanoes, erupting with such violence that they could hurl material hundreds of miles above the moon's surface. Io was revealed to be the most volcanically active body in the solar system, its surface constantly renewed by sulfurous eruptions powered by the immense tidal forces generated by Jupiter's massive gravitational field. This discovery of active volcanism on Io represented one of the most significant findings in planetary science history, and it was made possible only by the unprecedented close-up views that Voyager 1 could provide. No Earth-based telescope of the 1970s could have detected these volcanic plumes, yet here was a 1970s spacecraft operating millions of miles from home, revealing geological processes that were reshaping our understanding of how planetary bodies evolve and remain active over cosmic time. Following its Jupiter encounter, Voyager 1 used the giant planet's gravitational field to accelerate towards Saturn, arriving at the ringed planet in November 1980. The Saturn encounter represented perhaps the most visually spectacular phase of the entire mission, as Voyager 1's cameras captured images of Saturn's ring system with a clarity and detail that had never been achieved before. The intricate structure of the rings, composed of countless individual particles of ice and rock, was revealed in breathtaking complexity. Voyager 1 discovered that Saturn's rings were far more complex than anyone had imagined. What appeared from Earth to be a few distinct rings were actually composed of thousands of individual ringlets, separated by gaps and maintained by the gravitational influences of small shepherd moons that acted like cosmic traffic directors, keeping ring particles in their proper lanes. The spacecraft identified several of these shepherd moons, tiny worlds that played crucial roles in sculpting and maintaining the ring system's intricate architecture. The encounter with Saturn's largest moon, Titan, proved to be another watershed moment for planetary science. Titan had long been known to possess an atmosphere, but Voyager 1's instruments revealed this moon to be far more complex than anyone had suspected. The spacecraft's measurements showed that Titan's atmosphere was not only thick, but composed primarily of nitrogen, making it remarkably similar to Earth's atmosphere in basic composition. This discovery suggested that Titan might harbor complex organic chemistry and possibly even liquid methane lakes on its surface, making it one of the most intriguing worlds in the solar system for astrobiological research. The precision required to execute these planetary encounters using 1970s technology cannot be overstated. Each approach had to be calculated months or even years in advance, accounting for the gravitational influences of multiple bodies and the exact positions of planets along their orbital paths. Course corrections were possible, but they required precious fuel and could only make minor adjustments to trajectories that had been fundamentally established at launch. The fact that both encounters succeeded flawlessly was a testament to the extraordinary skill of mission planners working with slide rules and early computers. Meanwhile, Voyager 2 was following its own remarkable trajectory, taking advantage of the same rare planetary alignment to visit worlds that Voyager 1 would never see. After its own successful encounters with Jupiter and Saturn, Voyager 2 continued onward to Uranus, which it reached in January 1986. This encounter was particularly challenging because Uranus lies so far from the Sun that solar heating is minimal, creating extremely cold conditions that tested the spacecraft's systems to their limits.
Voyager 2's images of Uranus revealed a world unlike any other in the solar system. The planet rotates on its side, likely the result of an ancient collision that knocked it over, and its magnetic field is tilted at an extreme angle relative to its rotation axis. The spacecraft discovered additional moons around Uranus and revealed the planet's ring system, which had only recently been discovered from Earth through stellar occultation observations. The final planetary encounter of the Grand Tour came in August 1989, when Voyager 2 reached Neptune, the solar system's most distant giant planet. This encounter represented the absolute limits of what 1970s technology could achieve, as the spacecraft was now so far from Earth that radio signals took over 4 hours to make the round trip. Real-time control was impossible. Every action had to be pre-programmed and executed autonomously by the spacecraft's primitive computer systems. Neptune proved to be a dynamic, active world despite its great distance from the Sun. Voyager 2 discovered the planet's Great Dark Spot, a massive storm system comparable to Jupiter's Great Red Spot, and revealed wind speeds that were among the fastest measured anywhere in the solar system. The encounter with Neptune's largest moon, Triton, revealed another fascinating world, with geysers erupting from its south polar region, spewing nitrogen gas and dark particles high into the thin atmosphere. As both Voyagers completed their planetary encounters and continued their outward journey, they had fundamentally transformed our understanding of the outer solar system. These achievements, accomplished with technology that predated personal computers, demonstrated the extraordinary potential of human ingenuity and careful engineering. The spacecraft had traveled trajectories of incredible precision, threading gravitational needles with accuracy that would be impressive even by today's standards, all while operating systems that had been designed and built before the advent of modern electronics. After completing their planetary missions, both Voyager spacecraft faced a challenge that no human-made object had ever confronted: surviving and operating in the vast emptiness between the stars. What began as a 5-year mission to explore the outer planets had evolved into humanity's first attempt at interstellar exploration, pushing 1970s technology far beyond its original design limits into realms that existed only in science fiction. The story of the Voyagers' continued operation decades into their journey represents perhaps the greatest testament to the ingenuity of an era that dared to build for eternity. As the Voyagers departed the realm of the planets, they entered a race against time that continues to this day. Their nuclear power sources, those remarkable radioisotope thermoelectric generators that had seemed so advanced in 1977, were slowly but inevitably losing their ability to generate electricity. The plutonium fuel that powered these generators has a half-life of 87.7 years, meaning that power output decreases predictably over time. From their initial output of over 400 watts each, the power systems had declined to less than 200 watts by the 2020s, forcing mission controllers to make increasingly difficult decisions about which systems to keep alive. The power management challenge showcased the incredible foresight of 1970s engineers who had designed systems with sufficient margins to operate for decades beyond their planned mission life. Every component aboard the Voyagers had been over-engineered for reliability, using redundant systems and conservative design approaches that prioritized longevity over cutting-edge performance. This philosophy proved prophetic as mission controllers began the delicate process of shutting down non-essential systems to conserve power for the most critical functions.
One of the most poignant moments in this power conservation effort came when Voyager 1's camera system was permanently shut down after capturing its final image, a photograph of Earth taken from nearly 4 billion miles away. This image, showing our planet as a tiny pale blue dot suspended in the cosmic darkness, became one of the most iconic photographs in history. Yet it also marked the end of Voyager's ability to show us what it saw. The camera shutdown was a calculated sacrifice, trading visual documentation for the chance to continue scientific measurements in the previously unexplored realm between the stars. The transition from planetary exploration to interstellar science required the Voyagers to detect and measure phenomena that had never been directly observed before. As they traveled farther from the Sun, the spacecraft entered a region where the solar wind, that stream of charged particles flowing outward from our star, began to encounter the interstellar medium. This boundary region, known as the heliosphere, represents the edge of our Sun's direct influence and the beginning of truly interstellar space. Detecting the crossing of this boundary required instruments sensitive enough to measure subtle changes in the properties of charged particles and magnetic fields, all while operating billions of miles from Earth with electronics that predated the personal computer revolution. The Voyager particle detectors, built with 1970s technology, had to distinguish between particles originating from our Sun and those from the galaxy beyond, a task that required extraordinary sensitivity and stability over decades of operation. Voyager 1 crossed into interstellar space in August 2012, followed by Voyager 2 in November 2018. These boundary crossings were detected not by dramatic visual changes, but by subtle shifts in particle measurements that revealed the spacecraft had finally escaped the bubble of solar influence that surrounds our planetary system. The data from these crossings provided the first direct measurements of conditions in nearby interstellar space, information that could never be obtained by Earth-based observations or theoretical models alone.
The communication challenges faced by the Voyagers in interstellar space pushed 1970s technology to its absolute limits. Signal strength continued to decline as the spacecraft traveled farther from Earth, following the inexorable inverse square law that governs electromagnetic radiation. The 22-watt transmitters aboard each spacecraft, equivalent in power to a bright household light bulb, were now attempting to communicate across distances so vast that their signals arrived at Earth with less than a billionth of a watt of power. Maintaining communication under these conditions required not just the massive 230-foot antennas of the Deep Space Network, but increasingly sophisticated signal processing techniques that extracted meaningful data from what was essentially cosmic whispers. The global positioning of these antennas in California, Spain, and Australia ensured continuous coverage. But even with this worldwide network, communication windows were becoming increasingly precious as signal strength continued to fade. The spacecraft themselves demonstrated remarkable resilience in the face of technical challenges that would have ended most missions. In 2023, Voyager 2 experienced a potentially mission-ending problem when its main antenna drifted off target by just 2 degrees. At a distance of billions of miles, this tiny misalignment was enough to completely sever communication with Earth. However, the foresight of 1970s mission planners proved crucial. Voyager had been pre-programmed with automatic correction sequences that periodically realigned the spacecraft without ground intervention. Sure enough, the spacecraft corrected itself, and communication was restored, demonstrating the robust autonomous operation capabilities built into these remarkable machines.
Voyager 1 faced its own crisis when a software malfunction caused it to route data through a deactivated computer system, resulting in garbled transmissions that took months to decode and understand. Mission controllers, working with documentation and software tools that were decades old, had to essentially reverse engineer the spacecraft's behavior to diagnose and correct the problem. The solution required uploading new software to a computer system that had been designed before modern programming languages existed, using communication links that took over 22 hours for each message to reach its destination. Perhaps most impressively, NASA engineers have developed solutions for problems that won't manifest for years to come. The Voyager's attitude control thrusters, essential for maintaining proper antenna pointing, face the gradual buildup of propellant residue that could eventually clog their tiny nozzles. Working with thruster technology that predates modern materials science, engineers updated the spacecraft's software to extend thruster firing durations, reducing the frequency of operations and extending their operational life by an estimated 5 years. The longevity of the Voyager missions represents an almost miraculous extension of 1970s engineering. Designed for a 5-year mission to the outer planets, these spacecraft have now operated for over 40 years, traveling farther from Earth than any human-made objects in history. Their memory systems, with storage capacity equivalent to about 13 millionths of a modern smartphone, continue to collect and transmit scientific data. Their communication systems, operating at data rates roughly 138,000 times slower than today's internet connections, still maintain contact with Earth across the vast gulf of interstellar space. Current projections suggest that communication with the Voyagers will likely end around 2036, when their weakening power systems will no longer be able to operate the transmitters needed to send signals back to Earth. This gives us perhaps another decade to receive data from humanity's first interstellar explorers, a remarkable extension of missions that were originally planned to end in 1981. Even after communication ends, the Voyagers will continue their eternal journey through the galaxy, carrying their golden record messages toward distant stars they will encounter thousands of years from now.
The Voyager missions stand as perhaps the greatest achievement of 1970s space technology, demonstrating that with careful engineering, ambitious vision, and a willingness to push the boundaries of what seemed possible, humanity could reach beyond the known world and touch the stars themselves. These twin ambassadors, built with slide rules and determination, continue to expand the frontier of human knowledge, sending back whispers from the cosmic deep that remind us of both our cosmic insignificance and our remarkable ability to transcend the limitations of our small blue world. In an age of rapidly advancing technology, the Voyagers serve as enduring proof that sometimes the most profound achievements come not from the newest innovations, but from the timeless human desire to explore the unknown, no matter how distant or challenging the journey might be.